related to how to monitor on the victim machine and how to do some bunch of other things. But there is a problem with all those approaches. The problem is that all previous codes need some sort of file present on local file system, which means that if I am going to target something, I have to drop some sort of binary on that machine. No, audio is not muted. Uh, is everyone able to hear me?
Yes, I think his audio is muted.
Yes.
Okay, great. So in previous sessions, we had to drop some sort of binary on the local file system, and there are various problems associated with that. So first is that new file can be spotted in regular system monitoring. For example, we were using I notify, FA notify sort of stuff. Second thing is that if we are creating a file, downloading, writing a file will trigger security monitoring and will get scanned eventually. This is going to raise security alerts on antivirus software. So this is another problem. Third one is that the dropped file can be copied out of system and analyzed on some sort of sandbox environment, which means that malware analyst can capture the binary and analyze it elsewhere to figure out what we are doing. And we are not willing to deal with these problems. We simply want to avoid them. So we have a magical solution to that, and that is called fileless malware. Fileless because it does not create any file on local file system, which means everything remains in memory and is run from memory, which means that many times there won't be any file to copy out of system, no file to scan. So here we are able to deal with this. So what we will look at that how to uh, keep things in memory and try to run from there. Now if you want to do fileless stuff, there are bunch of options under Linux. Again, this depends upon kernel version we are using. So if kernel version is 3.17 or above, we can use memft system, which creates anonymous file entirely within memory without touching underlying file system. Second one is that SHM file. This one is available even in older versions. So this is SHM file. This needs dev SHM to be mounted as DMPFS, but is not guaranteed to be present on the system you are targeting. So you need to be careful with this one. For one, that we need to check kernel version, that we will see soon how to do it correctly. And if kernel version is below this, then we are limited to this. and even then this particular path may not be available on all the systems. So uh, there is another option, that is you can use tmp or /var/tmp delete file after dlopen or execv. The downside is that this will create a broken sim link in /proc, which will be telltale sign. However, you won't be writing anything on the disk for /tmp stuff. But here there is another problem, that if you are going to use this, if using this ensures that /tmp is mounted as tmpfs, this may or may not be the case. If I have a large hard disk but a small RAM, I may go for /tmp on the physical file system itself. So here you need to be careful with this one. Again, this one is very shitty way of doing things. This is not really fileless. This is also not really fileless, but the thing is that not many people bother to check this particular path, so we are counting on that. This first one is the truly fileless version. So once we are done with this, what we do, that here we can do a lot of things. One is obviously run malware from memory memory buffer. Now this has some interesting consequences. The consequences is that I can keep local copy of malware in compressed format, decompress in memory, and run from there. Now, if you think that this is familiar, you are right. This is something a packer will do. Similarly, the local copy of malware may be decrypted in memory, and run from there. Again, this looks possibly familiar to you, and this is what we call cryptor. Again, these are not the only mechanisms how these things work, but this is one of the many possible mechanisms. This is very simple one to code, especially if you have this, or at least this available. Now, in upcoming sessions, we will also see how to do this compression and encryption, even if this particular thing is not available. So we will be doing something like this, but entirely in user space on our own. That is something that we will be covering in upcoming sessions. But for a basic quick start, this is how we can do it very quickly without too much effort. Any questions so far? You are saying that everything remains in memory, but we also take memory dump for forensics. So in that case, how malware author hide itself? Well, if you are going to take memory dump, so of course you are going to get everything that is in memory. That means that a copy of malware that is running from memory buffer. But again, there are ways to hide there as well, but that relies on mutation engines and self-modifying code. So there are basically techniques where the malware does not decrypt itself completely. It will decrypt itself only part by part, and only those parts will be decrypted which actually need to run, and everything else will remain encrypted. And as soon as decrypted parts job is done, it will be the decrypted copy will be removed from memory again. So there are things like this which will make your life little bit difficult, but again you can take repeated snapshots of entire memory and hope that at different times you will get different parts of malware decrypted, and you can somehow possibly combine them together to get a very good idea on what malware is doing. So again, there is not like that we can hide from every possible technique in the book. Similarly, it is also not like that you can detect or prevent every possible technique in book of malware developer. Okay, so yeah, there is that. Any more questions? Any chance that our code can be swiped to swap space after it is run? Oh, yes, there is always a chance, but if you are worried about that, there are ways to mark your memory buffer as unswappable, so that is not mapped out back to the swap. So if you are worried about that, possibly you should be finding which pages are going to hold your memory buffer and mark them accordingly, so it doesn't go into swap. Any more questions so far? Okay, so we are moving on to the actual code and demo. And here, as I was saying, that we need slash tmp and dev shm as tmpfs. So here is very simple way to check for it. For example, if I run mount command, it gives me list of all mount points and the file system they are using as a list. And here what we can do that I can simply grab it with this particular string tmpfs, and here it will show all mount points which are using tmpfs. For example, here I am seeing that tmpfs on slash dev slash shm. So on this particular machine this is available mapped as tmpfs. We have some more paths like this which won't be actually accessible from normal user. Here we have slash tmp mapped as tmpfs instead of hard disk, so that is good. So here it is what we are going to use here. So wait, load from RAM. And so here what we will do that we are going to do something very simple here. In the first code we have two parts. One is shared library, second one is loader, which will load the shared library. Now here what we are doing that instead of loading it directly from here, we have done something interesting. For example, if I open this shared win.h, here you see that I have created a large array with name this. There are hexadecimal values, and in the end I have stored its length. Now here this thing that we have created here, this is basically content of this this particular shared object. So here what we are doing that instead of loading it from the hard disk, what we have done that we have created a buffer, stored the raw hex values in the buffer, and we will try to load directly from the buffer. Now if you want to know that how to generate this from this, there is a standard utility under Linux called xxd. So this is like this. I take this command, I pass -i, that will generate this header file sort of thing, and then I simply pass the file that I want to generate the header file for. So if I take it to, let's see here, this has generated the whole buffer and this length like this. Similarly, we can generate it for any file we want. This is very handy utility. So I use this, I generated this, and now we have to load it from the buffer. So load. Now here it is very simple actually. Our main function is very simple one. So here what we have done that This is the code that I have adapted from another code actually, so there is some extra code. Now here what I have done that I am decrypting it in the RAM. There is no decryption. There is no decryption in fact right now. So here what I have done that I have included this header file, and here in this I am creating a file entirely within memory, and then I am writing the whole content, that is this buffer with this much length that is generated here. I am writing it in this file that is entirely in memory, and then what I am doing that in next step I am trying to load the shared object from there, and the logic is very simple. Again here I check for kernel version. If the kernel version is 3.17 or above, here that means that file is created using memfd, and in that case I use this particular path from where I can access it in my own memory. Otherwise, if it is in slash dev slash shm, I access it using this particular path, and then using dlopen, I am able to load it. Now the kernel version is very simple one actually. Here what I have done that I use this particular function. This will return me the version string. For example, if I do something like this here, here it is giving me this particular version. So this particular string will be in this particular buffer. So here what we are doing that we are breaking the string across this dot, and then we are simply checking first two numbers what we are getting. So if first number is less than 3, return 0, greater than 3, that means it is definitely greater than 3.17, and then we check for second number. If it is less than 17, we can return 0, otherwise 1. So this particular kernel, this particular function does very simple thing. If the kernel version is 3.17 or above, it will return 1, otherwise it will return 0. So we use this. So here if the kernel version is 0, as in it is less than 3.17, so we create file in dev shm using shm open function. Otherwise we create mmfd create, and then we use this particular file descriptor to write our shared object, and then we finally load it using dlopen. Now here I have loaded the shared object plainly. I have not performed any encryption or any compression, anything, but here we can store this whole buffer in compressed format or in encrypted format. And here before we are going to write this in the file handle in memory, what we need to do that we have to simply decrypt this or decompress this, and then we will write it here, and then we will be able to load it just like we have done here. So nothing much will change. Any questions so far? Okay. Now if I run this, it is, yes, here we are seeing that module was loaded correctly. This particular string is coming from here. There is very simple function that will run every time it is loaded because I have marked it as constructor. So this particular string is coming from here because on load this is getting called and this is printing the string, so that we know that our shared library has been loaded properly. Now this is one way to do it. Now again, suppose I do not want to contain a copy of my, my malicious binary in a buffer. Reason being, if I have it in buffer and it is compressed, malware analyst can simply dump that part, decompress it, and analyze that. Or if it is in encrypted state, that means that I also have to keep the decryption key somewhere within my loader. So that means again some malware analyst may be able to dump the buffer, capture the key, and perform the decryption manually, and then analyze my actual binary. Now suppose I do not want that part. So what I will do that instead of loading from local buffer, the local copy that I have stored with me in compressed or encrypted format, what I will do that I will try to download it from some remote server. So that again is very simple. Here what I have done that this is my remote URL from where I am downloading it, and then I simply download it. Download function is very simple. I am using curl library. Everything else is just like previous code. There is no change. There is only change in this one. I wrote this particular code first. That one's after this, so that is why the both codes look very similar, and the previous code contains a lot of extra stuff. Now to download from this URL, I do not want to deal with protocol, so I simply what I do that I simply use curl library. So this part will be pretty much same for whatever you are using. These two particular lines are something you should be careful about. These are there to disable SSL verification. For example, if I am using my own HTTPS server with self-signed certificate, that is not going to uh, conform to the validation. So curl will simply stop downloading, giving me an error that SSL verification has failed. So just in case, I have added these two lines. So here what it does that it will download the file, and I have supplied a callback function write data to write uh, the downloaded data and the file descriptor. So when it will download the file, it will call this particular function with this many parameters. And here what I have done that I have simply called write function from glibc itself, which is a wrapper around writes as call. And I am simply returning its value to back to the curl. So that way the curl will know how much data has been written and how much extra data needs to be written back to the file. So once we have written it in memory based file, we simply do the same thing again. Again, we check for kernel version. We pick it from here or here, depending upon which particular kernel we are running, and we do dlopen on that local path, just like we did in previous case, and it will load the library just fine. Now the benefit is that it is going to download it from remote server every time. That means that if I want to update my binary, I just need to put the updated copy on the server, and on next iteration it will pull the updated binary. The downside is that it is going to hit the remote server every time it is starting up, so that will be flagged in network monitoring solutions that there is some sort of request is going on this particular URL. So these are the trade-offs. Now, if you want to test it, it is very simple. Actually, wait. Let me start dummy web server here. So here we have this, and now I try to run load, and again our module has been loaded correctly, and here we see that we got a download request from local host to download this particular shared library. So this code works indeed. Okay. Any questions so far? Okay. So this is very simple mechanism to keep the files within memory. Now, of course, there are many other ways like writing your own basic loader, but that is something we will be covering in future. There is another technique, rather very interesting technique that we can use, that is called file cloaking. So, file cloaking is something very interesting. So, what it does, suppose I have a malware. So, what I have malware file on first run, it will load the actual malicious code. On subsequent, it will load some innocent code, and it is not limited to executing the binary from that path. Even if you try to copy it somewhere, for example your external storage, what you will get is this innocent code, because this has been replaced magically somewhere between your user space and file system driver. So that way, if suppose there is some process and you see that it is running from some sort of path, and you go to that path, you see a executable binary, you try to copy it, you happily copy it, take it to other machine, you try to analyze it, and then you see that this code does absolutely nothing malicious. And even then you see that that particular process is running on supposedly victim machine and doing something funky. So most probably you will be like, okay, there is something else going on, maybe some other malware got injected into this process and so on. So this is a very effective technique to derail malware analysis actually. So we will be covering this, but before we cover this, we need to cover file system driver, because we will be writing a basic pass-through driver before we can pull this off. So if we see file system driver, so here what exactly happens, I already covered the basic architecture, how things are stacked one after another in Linux from your hard disk to user space. There is something called file system operations, and here we have functions defined for various operations. For example, if I go to my basic driver, now this whole pass-through driver's code has been shamelessly stolen from some Fuse tutorial. Actually, I simply downloaded the code and I basically used it pretty much as is for the sake of demo. So here, if we see here, this one, on left we are seeing the various operations that file systems are supposed to perform, and on right there are names of the functions which need to be called to do that stuff. For example, if I see for open, it says that for open action you need to call bb underscore open, and if I find this code, wait, so whenever a file is opened, it is going to call this particular function. Similarly, for read, it is going to call this, for write, it is going to call this, and so on. Here, what I have done, that I have not done anything special in my code. I have just taken request from upstream and I have passed it straight to Linux without any modification. So what I am basically doing, that I am taking the file system request from one hand, passing it to Linux on another hand, and you'll be using this particular code to perform file cloaking by adding some filters and checks. So here, to write a driver, we need to specify basically these many operations, and once we are done with this, we can run it and happily mount our file system. Now the file system drivers, there are basically two types of drivers. uh, One is kernel space driver, and second one is user space driver. And for user space, there is something called fuse, that is called file system in user space. So if we are using fuse library, we can write whole driver in file system like this. We do not need to jump into kernel stuff. But if we do not want to use this for whatever reason, we may go for kernel space drivers. For example, under uh, Linux, if we are using ext4 or ZFS or BTRFS, all those drivers are running at kernel space. Similarly, if I attach a pen drive, its file system gets mounted as NTFS or something. NTFS driver is actually implemented using Fuse. This is a very common example. This is NTFS 3G driver uses Fuse, and the another example, that is SSHFS. This is also uses Fuse. There was some tool for Google Drive and mounting it in Linux. That too was using Fuse. But other drivers like ext4, btrfs, these are generally implemented as kernel space drivers. So once we have this much code ready, we can test it in a very simple way. Actually, let me terminate it slash tmp, and here keeping testing it is very simple. I take the path that I want to map, and it is the path where I want to mount it to. So I do this, and if I let's test here again, I see same files just like I have here. So if I create some file here and I do this, oh wait, I do this here, I see that this particular file has appeared. So this is a very simple idea, and now if we want to unmount it, before unmounting we will just check what does it show in mount. So let us filter it using this, and here it shows that this particular path has been mounted on this particular path, type this. So if we are paying attention to this, we can see that fuse has been used to mount it. And now if we want to unmount it, we can simply do this like this and be done with it. Now here probably you already noticed that mounting and unmounting does not require root. So that is a very good benefit for us. This does not require root, but there is a problem with this one, and the problem is that uh, permission system is complete bonkers, that is very stupidly managed. And what I mean by that, for example, if I mount it again, wait, slash tmp slash testdir, and here we have this thing, and if I go to test dir and I try to remove this particular file, oh wait, rm test file, here it got repeated. If I try to create a file, here it says that operation not permitted. And even if I use root, even then it is not going to allow me to create a file here. The reason is that Fuse basically twists permissions some other way that is pretty retarded way, but here we are. So there are ways to deal with this garbage. Basically, you need to handle all the permissions in your Fuse-based driver manually, which I have not done here because we do not really need that to run our file cloaking. But yeah, that is something you need to be very careful about. So once we are done with this, we can unmount it with ar here and f user mount -u slash tmp slash testdir, and we have unmounted it. Okay. Are you going to share this video afterwards? Yes, every video is getting recorded and shared on YouTube. So if you want to revisit certain topics, uh, yes, you can go to YouTube and watch it again. And even then, if you got some doubts, you can drop me a mail. I think Animesh will share the email IDs with you. Okay. Any questions so far? Anyone got any questions? Okay, so I will take that as no one has got any questions and we will move on. So once we have our fuse driver running, we will what we will do that we will modify it for file cloaking. So what we will do that the basic idea is actually very simple, and the idea is basically this. So what we do that for cloaking, what we do that on open we check if we want to cloak, and then if yes, we open different file than asked for and return its file descriptor. It is as simple as that. So that is exactly what I have done here in open, because this is the function that is defined here for open call. And what I have done that if this particular path that I am getting in parameter, all the paths here that we get, we it is related to the mount point. So if I am getting this particular path, what we are doing that we are simply opening paths, opening this particular file instead of the one that is asked for. So if someone is going to open /tmp /test dir /test file, what uh, what was asked, wait, fd2, what was given, fd2/dev/shm slash test file instead. So this is the whole very simple thing that we are going to do. So on first run, this happens on first run, and this happens on subsequent runs. So what we want to do here that we want to copy some other file here at this particular path. Here what I have done that I have simply copied this driver as this particular file. So this is what we are going to do. So in this particular example, what I have done that on first I have inverted this. So instead of uh, this order, this is what happens on first run, and this is what happens on subsequent runs. So for example, file /usr/win/ls, this is here, and suppose if we try to copy it to /dev/shm/test file here, and we run it to be sure that okay, yes, this works. And now what we will do that we will simply map this to same dir. I will pass it -f here, so it will remain in foreground and print our messages. So cd test dir, and I create two tabs here. Now on first one, what I do that I call test file, and I get this particular output. And if I call test file here, it gives me different output because the binaries have been shared. For example, here if I run it again, so here I am getting completely different binary even though I am supplying exactly same file and path here, and this particular file is not even getting changed. The file system driver is simply passing me descriptor to something completely different file. So for example, if I do something like this, and then after mounting it, I run process from this particular path, and then I simply cloak the file to return some other content. So this will be running like this one. For example, in our case, the first invocation went as ls to show the file listing. But if you go back to this path and try to copy it, you will get a copy of this bbfs file instead of the one that was run on the first iteration. So even though they are showing the exactly same path, they are going to uh, show completely different behavior, and you will have a very hard time figuring out how exactly this happened. Most of the time you will be suspecting that the process that is showing funky behavior but the binary is innocent one. That means that some other process maybe tried to inject into it or did something like process following or something like that, but that will definitely not be the case. So yeah, this is file cloaking that we have done here. Okay, any questions? Yes. Ro- so how does one trace this back in case one finds a fuse like this mounted on a compromised system? Okay, for example, if we uh, suppose I do it like this, and here we are, and we want to see what is going on here. So suppose I see that there is some thing mapped on slash tmp slash dir, then I have to figure out which particular process that is running. For example, here if I check in running process and see here, so here I will see that this particular process is running, and now here I know the binary name, so I simply gave a filter of this. So but here suppose I do not know this particular name. So what will I do that here we have seen this particular path where the file system has been mounted. So what I will do that I will pass a filter to this particular string. So here uh, we have got one mesh, so we know that this is the PID that is managing this fuse file system. So what we will do that we will go to root here, we go to slash proc slash 38944, and we see CMD line. Okay, so here we got the command line argument, and what we do here that we do this, and here this will give us path to this particular binary that is running. So here we can go back to this path, take a copy of this particular file and try to determine what it is doing, and in reverse engineering you can uncover something like this rather easily. So once you see that something else is going on, so that we will know that this particular fuse driver is trying to cloak certain files. Now whether you are able to capture the original file that was run is something different. For example, suppose this particular path doesn't exist by the time you came to know about the breach. So what you will do that you will simply dump the offending process that is running, irrespective whether it was run from cloaking or not, and then try to analyze what is going on there. So suppose if I want to do that way, so what I will do that I will suppose I do here self, and here there is something called maps. So you can take a look on this and see the memory addresses where the binary has been mapped and all the libraries have been mapped, and then here you can see the permissions. For example, certain pages have X bit set. So those are the executable bits. So if you go here, so you will see that most of your code remains in these areas where executable bit is set. So if you take the dump of whole memory and use this to process the memory dump part by part, you will again end up with a sufficiently large chunk of code, and you can again reverse engineer it to determine that it is doing something like this, and this particular file was cloaked. So that way you will get to analyze this suspicious binary as well, even if it was cloaked using some sort of fuse driver or a kernel driver. I hope this answers your question. Any more questions? Okay, so here is a take-home assignment for you that you may try to attempt in your free time if you want to get your hands on it. So, as usual, I will be sharing all these codes via the website, and what you can do that you can try to merge the previous codes in a single binary that does a lot of things, from key logging, file system monitoring, and bunch of other stuff, and try to implement something like file cloaking, where you are giving different binaries on different runs. So for example, on first run it is running as a keylogger, on second it is running as a mouse logger, on third it is running as a file system monitoring tool using FA or something, and post that it is returning some innocent binary. So you may try to do this, and then if you are feeling brave enough, you can possibly use, wait, so if you are using feeling brave enough, you can possibly use something like this, and try to keep everything encrypted in the memory and try to load it from there. So do try it. Let me know if you are stuck somewhere. That will be a really nice exercise for all of you. If you are stuck somewhere, maybe we can discuss that in some separate session. So if anyone has got any questions, I am here. We will wait for a couple of minutes, and if there are no questions, we will conclude today's sessions.
Seems like no one having any questions. Okay, so I'm gonna unmute everyone. Give them permissions to unmute. Okay, anyone having any questions or stuff that you wanna share with us? You guys can unmute yourself now. No one had nothing. Okay. बताओ मिस्टर जी क्या कर रहा है, रैप अप कर ले या फिर वेट करें इन लोगों का?
नहीं रैप अप कर लेते हैं.
चलो ठीक है फिर. Thank you guys. You have the feedback form. Just share the feedbacks. And there is that for recordings, it's available, and for the course, it will be on the website. Just visit our website. Apart from these two, any other questions that you guys have? Recordings is available on YouTube. Just search for InfoSec Trainer. You will find it. Or just go to our website. Every single sessions have a YouTube link. You can go and follow that one. And based on the codes that you have seen today, it will be available to the page for fun with malware. Mohit, thanks. Yeah, thank you for your support. We're just trying to do something right now. Okay, guys, so wrap up. We'll see you later. And next session is scheduled. So you can visit our website to go through. And I put one more thing. I guess that will help many of you people. Let's show you quickly. So let's suppose you are not feeling good to go through our website all the time and look for the things. So just scroll down and you'll see there's two things. One is Google Calendar, one is iCal format. So if you're running a web calendar, just open Google Calendar. It will show you the entire upcoming talks, timings, and links. Okay. So this will be updating as soon as we're getting new talks. And let's suppose you already have signed up for some talks. You can download the iCal format. In your phone, you can just import it to your phone calendar. It might be Google Calendar or any. It will work just fine. Okay, so that is that. And we got one more questions. Okay, thank you. Thank you, everyone. See you later. Thank you, Mr. Ji, for taking sessions for today.
Thank you, Nimesh.
Thanks. Next one is upcoming with Himanshu, upcoming the series of exploit development. So if you're interested on that, you can watch the part 1 on YouTube. And for part 2, it will be scheduled on 11th of this month. So it's 2 days. You can get our stickers for Eventbrite, and link will be shared here. So you can just go and follow up. Shifty.eventbrite.com. You can register here, and every single thing will be available. Feedback form, just 1 second. You can submit your feedback to this link, bit.ly/addition2. So thank you for your feedbacks and stuff. If you wanna deliver a talk, just drop an email to hello@addition2.com. And most probably I'll be replying back on that email address. So so yep, that's the thing. So see you guys on 11th. Have a nice time. Stay safe. And just don't go out. Good night.